going to address the Procca theory carefully of the massive gauge field. But just to remind you why we have to do it now, well, sort of obvious, but just to remind you what we succeeded to do up to now, we actually constructed the standard model, the electroweak part at least, the electroweak theory being the SU12 cross U1 hypercharge gauge theory. With the protagonist, you first, when you have a gauge theory, you define your basic constituents, which we call the matter, quarks and leptons. The minimal standard model, I should say, with left-handed particles being doublets, right-handed being singlets. The maximum parity violation told us that we had to do that. The Lagrangian then, the standard model Lagrangian, the electroweak part, we can write like this. We can sum over all the fermions. These are my fermions. I have a left-handed doublet, and the singlets. Everything is hidden in the covariant derivative, okay? I just sum over the fermions, right? So I can put a sum, or it can be generic. So it's basically covariant Dirac-Lagrangian. The symmetric part. So here, the kinetic energy of fermions, and of course the interaction hidden in the covariant derivative where we spell. What else is needed? The kinetic energy for gauge bosons, okay. And we have SU2, we have 3 of them that we call, so there will be F mu nu. Remember, we have 3 of them, we have to sort of study a little more carefully the Yang-Mills theory of non-abelian gauge bosons, okay. Where the covariant derivative I sum over repeating index. So the U1 gauge boson is B, hypercharge is the U1 charge, and so on and so forth. And B mu nu then would be D mu B nu minus D nu B mu. And F mu nu A. There are 3 of them. If there are 3 potentials, there are fields, there's 3 fields, it would be D mu. Have you seen it before? Yes. You did?
Yes.
I wrote it, okay. It turns out that he had an extra piece, which is fundamental, which in SU2 takes the following form. With the same group structure constants, okay, epsilon AB, A mu B, A nu C. Where of course epsilon is just TA, TT is I epsilon T. Let me not write indices, this you know in your sleep. So, yes please.
What do you mean exactly with minimal standard model? Yes,
that's what I mean. That it's, sorry. No, I mean it's a good question. That it's minimal.
It's
because
it minimizes.
Minimal, which means you could write if I write you when you have a theory with some fundamental principle, think of Einstein theory of gravity, then you write the minimal theory. What is the minimal Einstein theory described by the minimal Lagrangian? Okay, you write the minimal version of that idea. So the minimal version means that, for example, I didn't introduce, which would be natural, think of the symmetry, think of today of neutrino mass. But I didn't introduce it because when it was constructed, the idea was to make it as minimal as possible, consistent with the gauge principle, okay? So we tried SU2. Look how I'm following minimality in a sacred manner. I exaggerate in a sense. I want to teach you to appreciate minimality. Nobody will start with SU2. Normally when you take the book on the standard model, they'll start with SU2 cross U1. I want to see how, you should sort of learn to appreciate it and then give it up when necessary, but think a lot. Because just by giving it up and adding stuff, okay, you won't learn. So for example, by pursuing the normality, you will see, I will predict that neutrino is massless. Well, at the moment I'm predicting that everybody is massless. By assuming that SE2 cross 1 gauge symmetry, I cannot write the masses. Any mass term will break the symmetry. So this cannot be the whole Lagrangian, of course. There is also, you know, let me write like this, we'll come back to it. After all, electron has a mass. And apparently up quark has a mass, and down quark has a mass. I don't know what I mean by that. Or you don't know, I actually know what I mean by that. But at this point, I don't know what I mean by that. It's a funny thing to talk about the mass of a confined particle. If it bugs you, you should ask me, okay? But it won't be now. We will discuss it later, okay? I have to include the masses. I do it reluctantly because I'm worried, you know. So, I put a question mark here. I'm worried about breaking the symmetry. Why am I worried about breaking the symmetry? Because in your homework, you learned that the massive gauge boson has a funny propagator, which I don't like, as it is. So all I wanted to tell you, we have a theory at our disposal, okay? And the first thing you and I will do, we'll start computing radiative corrections, so to confront it with experiment the way we did in the QED. It's that simple. You write down your Lagrangian, you have a certain principle to follow, and then compute. Just do it, as the Nike commercial says, and see what happens. But I can't compute it because my gauge boson propagator had a bad high energy behavior. I'm back sort of where Fermi was, and that's not good. I want to show you this, that actually construction of the theory, as brilliant as it was easier than what we have to do. So let's learn. Let's keep in mind, if I know how to live with these guys, if I can do the calculations, I would do it right now. We will compute, and we will do that. As soon as we learn, we'll compute something. Actually, we compute something before even we learn. So, what is a Broca Lagrangian? It's just like Maxwell. So I'm talking about a U1. Forget the fancy gauge symmetry with a gauge field A, but it's massive, so don't think of the photon, please, okay? Cannot be the photon. Or maybe one day, I'm sorry, I take it back. Someone measures photon mass. And I add a master. After all, this is the way to think about the Z boson. Now a few things. Why do I put a minus sign here? Remember where I wrote the scalar Lagrangian? It's very important. The scalar Lagrangian to the simplest field theory I can write is the field theory of a real scalar field, right? Let me make it free for simplicity. There's a positive sign here. Well, of course, you will tell me, who cares about the now, of course, you can say, who cares about the sign? The overall sign of the Lagrangian apparently is irrelevant, right? The Euler-Lagrange equations do not know about the constant or the sign I put. But there is a physical thing here. If I write this, I will have d05 square and so on. And it should cost me energy to move the field, right? It's a sensible thing to do. The kinetic energy I'm going to write with the positive. I want to be physical, okay? So if I put a plus sign here, why do I put a minus sign here in the Maxwell case? Remember? It's important. The relative sign. Now it matters because you will see that the propagators have an important opposite sign. It's a fundamental thing that I'll elucidate as we go along. Not today so much. Well, let's write it down in order to appreciate. This is minus a quarter d mu a nu minus d nu a mu d mu a nu. So it will have a minus a quarter, notice d0 ai d0 ai with a minus sign, because when I take the I component, there is no time derivative of the zeros component. It's not a physical propagating field, right? The time lag component, okay, that you know. The first thing that appears here, because it's anti-symmetric, is a space line, the I. And since AI is minus AI, I have a minus sign here in front. I have an additional minus sign. You agree? Everybody sees it. There'll be actually a factor of 2 because of the anti-symmetry. There'll be actually a factor of 2. So minus and minus give me plus. Minus and minus. So I will get 1/2 d0 ai. These are physical propagating field. I have the same sign as I had for the scalar field. So the sign is correct, and it's important, okay? This is the famous minus sign in the propagator, which is responsible, for example, for the form of the potential that I think Esteban asked you. You were asking me about the potential. We'll talk about that. That how do I, from my complicated field theory, write down the static potential between two, say, charged particles or two massive bodies in gravity. So let's rewrite. So let's rewrite a little bit this Lagrangian. You may have done it already in the homework. I can write minus 1/2 d mu a nu minus d nu a mu because it's anti-symmetric. Master, let me now just look at this for the time being. And I integrate this by part. Okay, I don't know how I did it, but I'm going to integrate by part. So when I integrate part, I drop the total derivative. So I get plus 1/2. I will get a box. Minus a mu, d mu, d mu, a mu. I'll get this. No. There was a plus sign, but upon the integration by part, differentiation by part, I get this. So that the Broca Lagrangian is 1/2 a mu box plus m squared g mu nu minus d mu d nu a nu. So a few comments. Where if I do the integration by part here, if I do the integration part, I will get 1/2 phi minus box minus m squared phi. Agree? There's an opposite sign. And this is why the propagator that you derive by the same rules behind the side. Let me call this MA. Well, I did. And then there will be this famous piece, G mu nu minus K mu, K nu. You did it by going into momentum space, right, where this is minus k squared k mu q nu. Then it's a simple exercise, which I presume, but now you've done. And you go this result. And this is what I don't like, and we'll be talking a lot about it. But before we do that, okay, so we have a propagator, okay. You see, how will you get the potential? Let me just wet your mouth, since you asked. You will get the potential from the force that comes from the exchanging the messenger, which comes from the propagator. The sign in QED will be opposite from a scalar theory. Anything that is scalar, if it's attractive, the QED will be repulsive. So if you have same charges, you will prove that the potential is repulsive. Okay, this should come out. You should be able to do that. You can see that because it's all, you know, whatever force I have, it's going to come from here. Through the, you agree, right? This is, after all, what Feynman taught you. Okay, the interactions come from the exchange of messengers. Okay, this is the beauty of modern particle physics. Okay, or beauty of modern physics. Whereas in this case, it will be scalar, and there'll be this interesting minus sign. Okay. A side remark at the moment. I'll come back to it. But what I want to emphasize today is an interesting equation of motion that we get from here. It looks like this. If you didn't write it, please write it down. That's an exercise. Any which way you want to do it, you will get this as an equation of motion. It's very similar to the QED, to the Maxwell equations of motion. Free, of course. Maxwell equation of motion, the only thing, of course, now that he has a master. Now notice what I can do here. I can take a derivative of this, d mu. If I take the derivative, d mu, what will I get? I'll get the box plus ma squared. Then there is g mu nu, so I'll get d mu a mu minus, this will become a box, d mu, okay, I should have a lower index, minus box d nu a nu is equal to 0. You're following me? Notice that the first term cancels. And we get an interesting thing. What used to be a gauge condition, a particular gauge condition in QED, which was necessary in order to eliminate the redundant degrees of freedom, here it came automatically out. It's an equation of motion. And it has to be, because this field cannot have 4 degrees of freedom. This is a spin, massive spin 1 particle. Okay, I can stop this guy, and then I can see that he has a spin 1. We'll see that. But I should have suspected it. So free, I get an important constraint as a consequence of Gaussian motion is that d mu a mu is equal to 0. And from here I get immediately the real equation of motion, Proca. What is a mu? It looks as a scalar field. It satisfies the same Klein-Gordon equation that the real scalar particle field does. So I have a sort of collection, of course, of propagating 4, it seems at the first glance, but there are not really 4. There will always be this condition, okay, which will eliminate to one, and it's a time-like we will see propagation, okay. In QED there were transverse degrees of freedom. We'll see that this guy has longitudinal because it's massive. But it doesn't have the force, the time-like one. So this is the celebrated Proca equation. And you see that you have the same sort of pole structure, the same propagation you had in the case of the scalar guy, times the Lorentz structure having to do Now maybe we can, okay, I'm going to erase this from time to time. I will write it down so for you to appreciate the simplicity, the elegance of the standard model. Lagrangian. If I think physically, if this guy satisfies the same equation in Klein-Gordon, then I could have said that dA mu nu, well, it's written here, okay, sorry. I would expect it to be the sort of, I don't know how to write it, I would expect the same scalar propagator, sum of all the possible polarizations, okay? If I were lazy, I would have guessed, okay? It would be nice that we check it. Times epsilon mu, there is a sum of the polarizations that you have to deal with it, okay? From 1 to 3. And this would be, of course, I over k squared minus the propagator. It's always like this, the scalar guy. This means that if I'm right, if this logic, this simple naive way of reasoning is correct, I can of course derive that. Then this should be minus g mu nu plus k nu over k. We'll check that. The moment the side remark. By the way, how did you derive the propagator for the scalar field? Just like the inverse of the quadratic form, or you actually use the formal field theory definition? The propagator really, a Feynman propagator, is this. Did you write this? Time order? No. Or you did? Okay. You can show that this is equal to with the I epsilon prescription, okay, that we'll talk about. The thing is to show that this is equal to this. Have you done that? It's a sort of fun to do, because this I can derive, so let me remind you, just that I write my quantum field as the usual integral over the modes. There is a normalization which we can check on dimensional grounds, if you wish. Then the creation operator, e to the minus IPX, plus, sorry, annihilation, creation. These are functions of P, dependence of P. They carry they carry dimension because you know it from the commutation relations. A dagger. Someone can remind me what the commutation relation is? Is a delta function. If I have different momentum. Sorry, A dagger. The blackboard is sort of. I can see the difference in 1 year. It's much less fluid. It's time to change.
It's a chalk.
It's a chalk also, maybe there. But these are, these are the, yes. The have to have better chalks. Okay, I gotta talk to them. So you can make a dimensional argument between convince yourself that you need this for dimensional races also. Okay. This carries dimension 1, this carries dimension, this carries dimension, this carries dimension, delta function carries dimension. You can figure it out. Let me not do it, okay? So I could just stick it in and I can compute this. And then you will get something like theta of x. You get these 3p over 2 pi cube. Because of the delta function, there will be two of them, so you will get 1 over 2e. And then you get e to the minus ipx. That's the first piece. Okay, time ordered, as you know, it has two pieces. Then there will be t theta minus x. 0, sorry. Theta is 0. It's time ordered, not x. And then the same integral e to the ipx. I guess. We don't have to do it now, okay? If you've done it, it's good that maybe we pause, something like this will come out. Then you can check this by doing the usual integral of p0, right? Choosing properly the complex contour with the pole prescription, okay? You're all familiar with this. Make sure, if you're not, that you become. So you see, I can as well confirm it now. If I write analogously mu, I would write it as the same integral d3p over 2 pi cube 1 over square root of 2. I would just do the same thing, right? A, which is p, epsilon mu of p e to the minus ipx plus a dagger of p epsilon mu star e to the ipx. I will expand in its Fourier modes the same way I did it for the scalar file. The only difference, of course, is a polarization vector. So therefore, it is not surprising when I go through the same exercise that when I'm going to have the sum is what is missing here. You see immediately that this will come out. I hope. Please try to see it, okay? If you have trouble, talk to me. Epsilon, simply because we have two of them. You pick them up, okay? And so this intuitive reasoning that what I am actually propagating is a bunch of scalar-looking propagators with their proper polarization tensor works, of course, it should. Just a digression. How does the fermionic propagator looks like in momentum space? Minus m, which is I, p slash plus m.
P square minus m square.
Same p square, sometimes I call it p, sometimes k. You see the same propagation. And if you remember, the sum of the polarization particles is p slash plus m. Which can also be the sum of the antiparticles moving in the opposite direction, okay? You would actually, when you do the propagator in the same manner, you have two pieces, one coming from u bar, but you think of the way the Feynman used to think of propagator, having particles moving in one direction or the antiparticles, okay? So you see, this intuitive physical reasoning works that my propagators are sum of the polarization of the spin states, okay? Times always has to be the scalar guys, okay? This was the cyclone, and I'm going to erase it if you don't ask me anything. Well, I'm erasing. So defining So let's just, for the sake of completeness, delta mu nu of A will be 0 time order A mu of x. By the way, sometimes you write often A nu of y 0, which I didn't write before because the propagate depends only on x minus y. Okay, you propagate from point x to y, and it's symmetric. I'm going that. That will give you this very easily. This will appear automatically. And the rest, of course, is showing that the pi zero integration picks up the right pole. You're sure we don't need to discuss it? You're all familiar with that. Okay. How you close the contour and so on. Okay. Any questions?
All of vectors in the Hilbert space are positive definitely.
Sorry?
All of vectors in Hilbert space are positive definitely.
Well, the physical vector components end up being positive definite, right? As we were saying, this is important. The AI. The I, the physical components, right? A0 is not.
But then fixing it using the condition.
Let's see. If you maybe let's write down the. Okay, let's do the following. Maybe it will help to then. You ask your question again. Let's look. Let's stop the guide. Let's go in the rest frame and let's write down what the guide looks like. What are these polarizations? What is physical and what is not physical? If you wish. Let's do that. See, I want us to, you have to be really, you have to be happy. I know that this propagator is bad. There is something wrong with the theory. On the other hand, it correctly describes the massive gauge field. It's also correct what I wrote, okay? It's somehow wrong and right, you know, as Nambu said, remember when I said the symmetry can be broken and broken, okay? This is what we got. We derived these equations of motion. We derived the propagator. It's correct. I don't know how to compute with it, but yet it correctly describes the physical properties of the massive gauge field. For example, this is what you're going to use if you calculate decay rates and stuff like that. You're not going to use that to do the loop simply because the thing will diverge, we said, right? Why shouldn't I have? Let's keep it here. The rest of the and once again, the reason I don't know how to compute is the second piece. When I go to very high energies, this propagator, as p squared goes to infinity, goes as 1 over mx squared. So the integrand is never going to vanish. And the integrand of my calculation is going to be propagators like this. And therefore the integrals cannot be finite when I look at physical processes. I could recalculate. Remember the other day? Well, let's check it briefly. We said, for example, this better be finite. There is nothing I can renormalize. Remember when I found out that this was sort of infinite, but I didn't worry because it was logarithmic, but it was infinite. Well, this was just sort of a quantum version of the charge I wrote. And a quantum version of the charge will not only have a one charge particle, it's going to have a cloud of particles and antiparticles around it, okay? So I should think carefully about what I call a charge, okay, in a quantum theory. But here, this is a scattering amplitude. There is nothing I can change. There is no Lagrangian expression here. There is no tree level, as we say, that corresponds to the scattering. That better be finite. When I speak of renormalizability, what I mean is simply that I can compute. That when I compute scattering amplitude, they are not infinite. Okay, it's that modest. And in QED we found out that it was finite. Now how would it look like here? Remember, I integrate over the internal momentum, properly normalized. I have two fermionic propagator. I ignore the mass of the electron, or whoever is inside, so I have a scattering of two fermions. Then I have two propagators, so I will have 1 over k squared minus ma squared, and then I will have this piece. The symmetric equation G mu rho will give me 1, P mu rho will give me P squared, no, K squared, minus MA squared. This is what I have, roughly, symbolically, okay? It's really weird. So notice here I can ignore MA. This is okay, it behaves correctly at high energy, it's okay. This is K squared, dk squared. So 1k squared cancels k squared. Look what I got. I got dk squared over k to the fourth from the first piece. So what I have when I square it, I will have 1. Then I will have something which is of order k squared over ma squared. Strictly speaking, the way I wrote, I will put a factor of 2, but I'm ignoring the Lorentz structure, plus k to the fourth plus ma to the fourth. This was QED, the first piece. It behaved beautifully, right? I integrate k from some minimal energy of the process from the mass by ignoring the mass here up to cutoff lambda. Okay. This is what you end up in this schematic manner doing. You will learn as you go on with size. This is how you compute things. So QED didn't have these pieces. And this manifestly vanishes when lambda goes to infinity. We go to 1 over lambda squared. But look at this piece here. This is the culprit. Okay? It goes as 1 over ma squared. No, ma to the fourth, sorry. And then k4 cancels k to the 4. And I have an integral dk squared, so I will get lambda squared minus whatever is the small quantity of order of the scale of the process. Okay? I don't care. Terribly divergent, quadratically. Extreme sensitivity to large scale physics. So this sensitivity to cutoff, if you wish, think of that as sensitivity to some new physics which is beyond that. Okay? The renormalizability, the capability to compute means simply that what I'm doing now, I can ignore what is happening at the moon. So a good approximation, this decoupling, this is very important. If we could not live like that, right, we would go crazy. So in order to do calculations in physics, I should be able to ignore the new physics which happens at very high energies. Okay, when Newton computes the motion of a whatever, or a projectile, okay, then he can ignore, and you and I can ignore the relativistic effects. Simply here, the large-scale physics should disappear when the cutoff, when the new scale goes to infinity. I should recover my original theory. Here I get the opposite. Okay, this is the problem that we have to somehow solve. Okay. Meanwhile, let's go on and study the massive gauge field. The more we know about it, the more insight we will have in how to deal with it. So let's take A at rest, which is useful when I want to compute, say, the decay rate, and we should do that. So what happens at rest? The only quantity describing a particle is the spin. What are the spin 1 generators? Someone can help me?
Davis something?
Right.
Davis.
It is easy to check that the structure constants provide the proper generators. All you have to, well, this satisfies the same commutation relations. For example, T3, which I normally diagonalize, is this form. You can call it S3 if you will, to emphasize that it's spin. If it's at rest, it's spin. Polarization of this particle is what we talk about. It's going to be given by the spin. You can say I could, well, you're not saying it, but you could ask me, why don't I use the diagonal T3? As you know, what we did with spin half, in the case of spin half, I take sigma 3, which is diagonal. By convention, okay? This circle I can diagonalize, right? By performing a unitary transformation, I can diagonalize. I can solve the eigenvalue problem if you wish. We'll do it in a second, okay? When I diagonalize it, I know immediately how will it look if it's diagonal. What are the eigenvalues of this guy?
1 and
1 is 0. The others, determinant is minus 1. Therefore, the eigenvalues are 1 and minus 1. The trace is 0, and determinant is minus 1. So, I'm going to use this and not this. Do you know why? After all, I should have that freedom, right, with which this is just a choice of representation. It seems I should have the freedom. Well, the answer is no, because I've used my freedom here. I've decided, when I define our Pauli matrices, psi, the doublet, transforms like this. With a proper choice of Pauli matrices, which sigma 3 is diagonal. So in this case, a vector field Vi must transform as the vector field. How do I build a spin 1 representation? I build it from spin half. This is a doublet. Why don't I call this U? Usually psi I call the 4 component. And U dagger sigma U behaves as a vector field. You know that, you know it, you knew it always, but maybe you don't sort of keep it in your mind. You know, this is SU2 that I talk about, it's simple. You know it, for example, from, look, when you write this in QED, right? This guy is a 4 vector, but the space components are 3 vector. This is psi dagger, gamma 0, gamma mu, psi a mu. This is a good moment as any other to decide my G mu nu is diagonal. I may need it now, so why don't I say it? I hope we use the same. I'm pretty sure, right? The other with the opposite sign is very rare. We've given up imaginary time long ago. Okay? My advisor used to have imaginary time. I guess crazy. And my gamma 0 is this. It's off diagonal. It's very useful for relativistic calculations. In non-relativistic case, we used to take it actually diagonal, if you remember. And gamma I are simply Pauli matrices. Sigma I minus sigma I0. So the gamma 0, gamma mu that you have here, let me write it here, is psi dagger gamma 0 will give me sigma mu bar, we call this 0 sigma mu psi A mu. Sigma mu is indented because it's sigma 0 sigma I, and sigma mu bar is sigma 0 minus sigma I. This is sort of a two-component notation which is becoming more and more popular. So notice that the space part is precisely what I wrote. You sandwich sigma in between two, and psi, of course, is a four-component spinner made out of two spinners, okay, that we call UL and UR. Okay, let's as well write it in this picture, gamma 5. I'll take with this sign, it's defined after a sign, and I'll take it to have this sign. So the upper component I will call left, and I'm going to call it 1 plus gamma 5. In this thing, L is 1 plus gamma 5 over 2. So in the two-component space, you get precisely this. This behaves as a vector. So I have an exercise. I could do it here, but I don't. We should finish around 11, right? Where we started a little late. But you got to, no, 11, which will be 12. You got to leave. What time do you want to leave?
What time was it?
So this is wrong.
No, it's okay. It's just they change time. It's just set an hour.
Plus 1 hour.
Yes, please.
11:45? No, 12:15.
12:10, like this.
12:10 you should leave here, right? Okay, we'll finish in time. So I have a little exercise. Show, please, that this is equivalent to this. Okay, I'll sketch it. Maybe I just sketch it here, it's easy. How does U dagger sigma I transform? Well, I know how U transforms. So this goes as 1 plus I sigma k, say theta k over 2 sigma I, 1 minus I sigma k theta k over 2. So the first piece is U dagger sigma I U. Then I get plus U dagger. Then I get I sigma k theta k over 2 commutator with sigma I. Correct? And the rest is easy. Epsilon ijk is coming out. Please convince yourself. Okay. This will you will get the epsilon ijk, but this will be equivalent. On the other hand, this is some vi, and vi should transform as 1 minus I define I theta k dk ij vj. 1 means that ij is delta ij. This, confronted with this, will give you the form of the generator. I have to use it. This is very important. Okay. This forces the form of. There is no arbitraries anymore. This is the same as saying that from the spin half you build all other representations, okay? In a well-defined manner. But there is freedom in defining spin half, the rest then follows, okay? So once we made a choice with Pauli, so this is correct T3. I have to find my eigenstate. That's very easy. T3 acting on 0, 0, 1 gives me 0. You agree? This is the zero here. So this is one eigenvector. T3, take this one. 1, I0 will give me minus I times I is 1 will give me this. This is this. T3, 1 minus I0 is minus 1. It's easy to see. Remember that we derived that P mu epsilon mu is 0, is equivalent to d mu a mu is 0 by our Fourier transform. So I can write now the physical polarization states. There is epsilon plus and minus. I normalize it. I put 1 of square root of 2. I write down them horizontally because that's how we are used to. 0, 1, plus or minus I, 0. These are these two. 0 is necessary here because the guy is at rest. So what we are saying that epsilon 0 must be 0 in all of these polarization tensor. Whatever polarization I take, epsilon 0 must be 0. It's very simple. It's just a spin. It's just these three guys. Okay, I write them horizontally. And then there is epsilon, we can call it 0. This is often called transverse and longitudinal. We'll see in a moment. This will be 0, 0, 0, 1. Only 3 of them. The sort of, the time like one, I don't know how to call it, which would be just, which would be, the fourth one would have to be orthogonal to these, right? Would have been the one which is orthogonal would look like this. You agree, the time like one. However, this condition kills it. Okay, this is very important. We got rid of the unphysical guy automatically from the equations of motions. It had to happen because there was no gauge freedom. In QED, we have to figure out what to do. Okay, we fix the gauge as we were taught. I can boost this, and the boost is conventionally done in the z direction. For simplicity, if I boost it, so boost do you agree that these guys remain unchanged in the z direction? That's why they're corrector. Transverse, these guys are perpendicular now. Now the name is justified because I want to boost in the z direction, okay. So now epsilon t, which is this what I call plus or minus, is the same, 1 over square root of 2. 0, 1, plus or minus I, 0. And the third one, the longitudinal one, see the name now will be good, which had this 0 eigenvalue. Can you guess, or shall we do it? Well, epsilon 0 prime is epsilon 0 minus v, let's say plus v, let's go in this direction, v epsilon 3, square root of 1 minus v square, right? Epsilon 3 prime is epsilon 3 plus v epsilon 0, 1 minus v square, but epsilon 0 is 0. So epsilon 3 prime is epsilon 3 divided by this. So let's write in here 0, this remains 0. Epsilon 3 prime, what is this 1 over? That's E over M, according to Einstein. Agree? This was 1, this is now E over M. C is 1. And what is this thing here? Epsilon 3 prime, V over this is momentum. This is P over M. P in my notation is P3. I have boosted in the Z direction with this sign. These are my polarization tensors. This is what we have to use. We can rotate them, we can boost them in any direction if we wish. But we can also fix this to be the moon of when the guy moves. Okay, we'll see whether it's necessary or not, depending on the problem. And since the guy was null, the timeline component, it remains 0. Yeah, I can simply ignore it. I got these 3 physical degrees of freedom. Notice when I go to very high energies, maybe just a side comment, okay, often it will be interesting to go to high energies, okay, or maybe it's the right moment to say it even, and not just a side comment. If you go to very high energies, if P is much bigger than M, then E, which is square root of P squared plus M squared, is roughly P. So I can, in this thing, epsilon L goes basically mu into P mu over M. Energy and momentum are basically the thing when you're at very high energy. Okay. And this is what I used to worry about. You see, you can see it from this point of view, but I worried in the propagator. I got in the propagator the thing that I didn't like, but you can see it here when the longitudinal guy is very, very, very fast. I get this strange propagator. It doesn't decouple, right? It becomes larger and larger, not smaller and smaller. And yet I say, and maybe this is a very important thing to say, that Feynman, who was not completely stupid, please look at some of the videos today of Feynman, to appreciate. If, forget the brilliance of physics, the intelligence of this guy, the clarity of thought, it's amazing. There is a thing that should be done as a sort of mandatory teaching. There is a 7-minute video on magnets by Feynman. I advise you strongly to have a look and then we discuss about that. Okay, it has to do with a profound question. What does it mean to ask the question why something happened in physics? This can teach you a lot. Not to be fooled by false prophets, okay? And Feynman used to work. I told you, and maybe Safe already told you, that in QED there are even infrared divergences. When you go to very small momenta, you get problems. They're cured. In order to simplify his life, Feynman used to work with a massive photon. He would give a photon a small mass, and at the end of the day take the limit. And he used to get the right result, but it looks crazy because how can he get the crazy look? I'm getting a degree of freedom which is becoming more and more problematic when I go to higher and higher energies. And that's what he was doing. And the reason is that in QED, the current is conserved, which is equivalent to saying that P mu, J mu is 0 in the momentum space. Which is like saying psi bar gamma mu psi is 0 in the momentum space. And that's what the guy couples to, right? This is what the things you're computing. So the longitudinal degree of freedom doesn't contribute. If your theory has a conserved current, in other words, if you have a gauge symmetry, and we don't want to have a gauge symmetry, we want to talk about massive gauge boson ZAW, we want to break that symmetry. Current will not be conserved, we will see. Then I will have a trouble. Okay. This particularly happens in non-abelian gauge symmetries, okay. It was realized around 1960 by Weltmann, who was an advisor of Hooft. You must have heard of this name, right? A Nobel Prize winner who had one dumb in 1960 realized that whereas in QED, where the current is conserved, you see this degree of freedom. So you would write here epsilon L mu psi bar gamma mu psi, and this would simply be 0 for an energetic guy. Any piece that, and this is why when you write the proton propagator, another thing is when you write the photon propagator, right, then we said that we have G mu nu minus I over K square, and then we have minus the gauge dependent piece. None of this matters. That's why you can choose any gauge you like, because at the end these degrees of freedom proportion to K mu simply decouple. Okay, this is the meaning, okay? Here there was f of psi, K mu, K nu over K squared. I don't have to worry about this. Another reason why Feynman, for example, used this gauge, because it was a simplest gauge to use, and he knew he was going to get the right result. Okay. Well, you and I will have to work. I can tell you immediately because the current will not be conserved. That's why I keep emphasizing this. This I will leave. It's easy to check what sum of epsilon mu star is. Sum of these 3 degrees of freedom. I said that this must be equal if I'm right. Remember, in order to get the correct propagator without doing the calculation, I should get this. And for example, it's for example 0, 0 component should give me -1 plus K0 square over MA square. And what do I have? I get, well, where I get a, this is equal to, sorry, I call it P. P is K. All right. And this is equal to P3 square, if you wish, or P square over MA square. Right? K3 square, or K square. K0 square, which is energy square, is MA square plus K square. But so if we check it, we can check some other component, for example, 3, 3. I will get +1. Remember my G's is -1, and then what is the 3 component? Minus E squared over ma squared. And that is, am I right? No, why am I writing this? Minus P3 squared, or P squared, or K squared. Sorry. No, plus twice the minus sign, Ryan, or whatever. I don't have to worry about the sign because I have both in the same direction, okay? And this gives me ma squared plus k squared over ma squared. And this is simply e squared over ma squared. Which is true, right? Twice this. And so on, and then you can check the others. Okay, I could just check to 1, for example, 0, 1. What will be 0, 1? According to this, I should get 0. And do I get 0, 1, 0? Yes. I take 0 component times the first component, it's always going to be 0. No. Yes. It's the same.
Yes, it is.
Yes, you have to sum over the same guy. This is a sum over the polarization test. Yeah, correct. Right? This guy has 0 component non-zero, but he has the first component 0. This guy has the first component non-zero, so on and so forth. It's very easy to check this relation. This is what we got. This is correct. Now we are. Okay, I've done this, I hope, slowly enough that you all follow me, okay? Some days will go faster, some days will go slower. See, once you know the polarization tensor, you and I can compute, for example, the decay rate. It may be very useful. Because if I compute the decay rate, say, of a Z boson, I can compare it with particle data group. It will be a great feeling for you to see how nicely the standard model makes one of the most impressive predictions, which used to be an important question: how many neutrinos there are? How many light neutrinos? I can count them by looking at the Z decay. Z decays into everything that couples to it. So if there are 10 light neutrinos that we didn't know, there could have been 55 generations, okay, or 10. Maybe in the old days, one. I've seen that there is more than one generation. You know, all hell breaks loose. You open a Pandora box. This magic number of 3, the first hint came from the Z decay. You could see that you couldn't, there was no room for another neutrino. Well, today we have LHC, we will talk about that. So how would I compute it? Maybe let's just outline for a few minutes and then I'll let you go, you have to run. So remember, this makes sure that d mu nu A, once again, is sum over epsilon mu nu times the scalar propagator. This is a very useful formula for any particle in question. If you know polarization states of a graviton, you and I could circumvent all this study, or maybe we should comment it next time, okay, just to show you the power of this reasoning that you and I could write the graviton propagator, okay, by thinking a bit about the physical states. A spin 2 particle, right? Graviton has to be spin 2. It's got 2 components. You mentioned it?
Yes.
That you did, right? Right. The graviton, the messenger of gravity.
Yes.
There are indications that it's there, we have to be sure, but or even see gravitational waves, right? These are exciting days. So for graviton, what you have here would be some of the polarization states. There'll be more than a bit more complicated, okay? So if I were to calculate the K of a gauge boson into F1, F2, two fermions, if it's an ultra gauge boson, it will decay into F1, F1 bar, or FF bar. In general, writing F1 and F2, for example, W will calculate, will decay into U bar D, right, or nu bar E. We know that Z will decay into E bar, E bar E, the way I wrote, nu bar nu, and so on. Now, the thing we should do in the first round, maybe that could be a homework to add a mass, but all these particles are quite light compared to W and Z. For example, if I want to calculate this process, or this process, whose masses you know, then I should set these masses to 0. Otherwise, I will have to go to higher number of loops by consistency. Okay, it doesn't make sense to be more precise than you can be precise. It's actually wrong. So we can take fermion mass going to 0, which simplifies things a lot. And then, if I have to decay, just to outline, I could give you this as a homework with some help. Then the interaction looks epsilon mu, F1 bar, gamma mu, A plus B gamma phi, F2. Okay, I should stop. 2 minutes. The most general one, for W boson, it's 1 plus gamma phi. For Z boson, I don't know what it is. It's some T3 minus Q. Remember, there was some function there. But this is the most general gauge boson interaction you should write. When parity is conserved, this gamma piece is not there. But we break parity in. And therefore, you and I can now, for example, do a calculation even by fixing the polarization of the gauge boson. We can say, why don't we compute what happens if my gauge boson is polarized? Okay, but of course it looks crazy. It will be useful to do it because I can then check. You see, since the guy is at rest, how do you do the decay rate? You take the guy at rest, it's simple. Then you can think of time dilation afterwards. You can boost it, okay? But you do it at rest. Since you can do it, you stop the guy. So you can tell me how you're going to polarize the W boson. You know, it looks very hard. You know, where is that magnetic field to polarize the W boson produced in a PP bar machine in 1983 and then decays immediately? Okay. It turns out we can polarize it, and I'll teach you next time. This is amazing. You know, this is the beauty of hadronic, energetic hadronic colliders, that we actually produce W's or these as polarized. And it's very useful because you need to have a vector in order to talk of parity violation. When the particle is not moving, the only vector is the spin. I need a sense of direction to be able to speak of right and left. Yeah, I can stop here. So the shoe guys can make it to your bus. Meanwhile, if there are questions, please please ask.
You have to stop.
Yes, I will, but if there are questions, I'll let it.
Recording.
I didn't get when you said we set the mass equals to 0. If we do it differently for the different particles, what about the loops or these?
Okay.
Well, we do the tree level, of course, but suppose you want to do the loop, you say. So I have a massive field decaying and I have a loop. So the loop correction here will bring me a factor of alpha, right, which is about 1%. Agreed?
Yeah.
Now look at the mass of the electron is 0.5 MeV. Think of the electron. What is the energy of the electron when Z decays into an electron?
Very high.
Yeah, but what? No, we can be precise, you and I.
40?
It's a half of the mass of the decaying particle.
40.
Because the guy is so heavy, so it's about 40 or even more, see, okay. Around 40, 50 GeV, okay. Let's say on the order of 50 GeV, so I have a nicer number.
Okay.
So notice that the corrections that you get actually are quadratic. You have to convince yourself, but that we can discuss. Not linear in the mass, they end up being quadratic. And then you get something which is what? I don't know. MEV over GV would be 10 to the minus 3, so I get another factor of 10 to the minus 5, 10 to the, it's an extremely small number, the order of 10 to the minus 10, right?
Yeah.
So I would have to go to 5 loops so that the mass, so you should set the mass equal to 0 at the precision that you're working. It doesn't make sense to include it. Now you may ask me, what about the situation when the Z boson decays into B quark? B quark turns out to be a bit heavier. It's about few GeV. Still the effect is less than 1%. So only if you worry about the loop, you can maybe include the B quark mass. And it may be interesting, we could do that, okay?
What is the precision that we have?
What is the precision that we have today? When in particulated group, they include the mass of the B. Yes, it's better than 1%. Now you have properties of the Z boson which are per mil, okay? So in that sense, at that point, I should include the mass of the B quark. Of course, the one thing we should have to include is the mass of the top quark, but it's so big that the guy cannot decay. Right? Top is heavier than W, you know that.
Yes.
Yes.
Answer.
So top can decay into W, plus a bottom or whatever, we'll talk about that, but not the other way around. So this is one mass that I will have to worry about. So it's good to do this calculation with the mass, okay? In the first run, we'll ignore the mass and then we'll include it, because a nice calculation to do when we can polarize the top, think about these things, is the opposite decay, in which surely you're not going to ignore the W mass. Now it's going to be very relevant. But in the first run, to get a sense of what is happening, and which is particularly good for the first generation, or for neutrinos, which are being seen. And the LSD, talk of neutrinos, is invisible decay. That surely you can ignore the neutrino mass. Okay, so this is very good to check the high precision invisible possibilities. Okay, you can set an excellent limit on the couplings of new particles if they exist. Okay, that's something done in that direction. But yes, I agree. It would be good to include the mass.
اكتب الأولى والباقي هتحط سبعة تساوي. ماشي. بس تخلص الأول بس الأول. ماشي. تخلص.
That's it. I can turn the thing off.